Okay, so I'm all right. We're recording. So we're looking at differential equations, chapter 7, and chapter 7 is covers an introduction to differential equations, and that's going to be important when you take the Math 282 course. All right, so take a moment to copy this example down. Okay, so let us see here. Now, why is this called a differential equation? This is an example of a differential equation. 2y double prime plus y prime minus y equals 0. Why is this called a differential equation? It's an equation because there's an equal sign, but this is a differential equation. I could write this equivalently like this, right? I could write this differential equation this way. What notation is this that I'm using? What notation did I use here? How many remember Leibniz notation for a derivative? Good, that's right, Nathan. Nathan actually almost, well, basically you beat me to it. Yeah, this is Leibniz notation. And the top differential equation, is Newton's notation. Question, Samuel?
Yeah, what are Newton's and Leibniz notation?
Newton's notation is like y prime. Leibniz notation for a derivative is dy dx. Two different notations for a derivative. Sometimes one is a little more convenient than the other. Okay, I'm sorry?
Okay.
Yeah, this is Newton's notation, the prime, and Leibniz notation for a derivative is dy dx. You've seen them both, right?
I have never seen Leibniz notation before.
Oh, wow. Wow, that's like traveling on the road and not hitting a red light almost. Well, I'll tell you, Samuel, I'm glad you're seeing it now. I'm glad.
Or at least the notation that I'm seeing right now.
Yeah, the y prime you're used to, and indeed maybe some professors stick to just using y prime. Indeed, maybe in calculus 1, that's what they stick to. But there is a second notation, and this is a differential equation here because it's an equation that has derivatives in it. 2 times the second derivative of y plus the first derivative of y minus y equals 0. That is an equation that involves derivatives, so we call it a differential equation. And what we want to do here, it says, well, for what values does y equal e to the rx satisfy this differential equation? When they say what values, they really mean, well, okay, what values of r? What r values will satisfy this differential equation? And so what we need to do is, well, if y equals e to the rx power, what would y prime equal? So they're demanding that y equals e to the rx power. What would y prime be by the chain rule? Right, that's right, Renaud. R times e to the rx power. And what would y double prime be?
R squared e to the RX.
That's right, Samuel. So you see, what we can do is we can take these, the y and the y prime and the y double prime, and what can we do with those in regards to this equation? What do you think we should do?
Substitute.
That's right. Good instincts, Nathan. Substitute those in the differential equation and then see if we can solve for r. And that's what we're going to do. So let me show you here. We've established what y and its first two derivatives are, and here's where we substitute them in the differential equation. Now we're hoping to solve for r. So really what this is an exercise in just understanding what a differential equation is. Okay, well, so here we are. And what I'm going to do, what we'll do is we want to solve for r. So e to the rx power is a common factor in all three terms. So you'll get e to the rx times 2r squared plus r minus 1. That product equals 0. And I want to solve for r. So, you know, either, I mean, this implies, actually, let me add something to this. Get that off there. I mean, if the product of these two functions equals 0, this means that either 2r squared plus r minus 1 equals 0, or that e to the rx power equals 0. Right? That's certainly true. Right? I mean, basically, we're using the idea here. We're using the idea that if a times b equals 0, right? If a times b equals 0, this implies that either a equals 0 or b equals 0, right? So it's the same principle here, what I have here. Same principle. Are there any questions on that? Okay, well now let me ask you, can e to the rx power, can that ever equal 0? No. So this equation here has no solution. This part here, that's right, Sean. This part here has no solution. But the equation on the left, 2r squared plus r minus 1 equals 0, well, that can have a solution for r. So if we factor it, if we factor that polynomial equation, we get r equals 1/2 or r equals -1. And therefore, y equals e to the 1/2 x and y equals e to the negative 1x, those two equations satisfy this what we call second order differential equation. It's called a second order because we have the highest derivative in the differential equation is a second derivative. So this is a second order differential equation. And we end up getting two solutions. So chapter 1 is just really an introduction to differential equations. Are there any questions on this particular example? Marcus, well, so in terms of factoring, I mean, this is, I mean, the 2r squared, the only way you can get a 2r squared is with a 2r times an r. So 2r times r. And then the negative 1 here, the only way you can get a negative 1 is by, so like 2r times r is equal to r squared, right? So that's how I get the 2r times r. And then negative 1 can be written as negative 1 times negative 1, sorry. Negative 1 times positive 1. So, I mean, here's a negative 1, here's a positive 1, and if you foil this, if you foil this out, you will get this particular polynomial equation, right? Remember how to do FOIL? FOIL is first, outer, inner, last. So first would be 2r times r. Outer would be plus 1 times 2r. Those are the two outer terms, right? Inner would be the two inner terms, negative 1 times r. And then the last would be the two last terms here, negative 1 times positive 1. First, outer, inner, last. That gets you 2r squared. And then you got a plus 2r and a minus r. That's a plus r, and then minus 1. So it checks out. So the way I learned how to factor was just to work through the combinations in my mind. I know there might be fancy ways or algorithms, but basically I just, if it factors, I can factor it, and, I look at them as like little puzzles. Okay, was this helpful, Marcus? You're good? Quick. Okay, good, excellent, excellent. All right, well, let's move on here. Let's move on then to another example, another differential equation. And here, hey, here's a differential equation. And this one is going to model a population. We can model a population with a differential equation. Okay, let me give you a moment to copy this example down. Okay, so let's look at this here. Let's look at this. So this this dp dt on the left here is a rate, right? It's a rate. And it's a rate of blank of blank. Okay, do you think you can fill in the what I'm looking for here? And maybe I'll give you a little hint. G here and P here. Rate of okay, growth is right, Renaud, for the second.
Growth of population.
And that's right. Was that Samuel who said that? Good. Rate of growth of the population. That's what this stands for. And they're saying that the rate of growth equals 1.2p minus 1.2p squared over 4,200. So first thing is, for what values of p is the population increasing? Well, under what circumstances would a population be increasing? If we think about the derivative, dp dt, you know what, like if a population's, okay, that's right, Nathan, that's right. So certainly if the population's increasing, okay, this would imply, okay, if the population's increasing, this would imply that dp dt is greater than 0. Absolutely. What about part B? For what values of p is the population decreasing? What's that imply about the derivative when the population's decreasing? That's right, dp dt is negative, less than 0. Right, are there any questions so far? All right, and we haven't, you know, found the population values that make these derivatives greater than 0 and less than 0, but we will. Now, what about equilibrium? When a population's in equilibrium, what's that tell you about the population? What's that tell you? I mean, what is, for a population to be in equilibrium, what's that mean?
It doesn't change.
It doesn't change. That's right. It's not growing or shrinking. That's right, Samuel. That's right, Renaud. So that means in that situation, dp dt will equal what? That's right, Leping, equals 0. So you see, by the fact that we can model this population with a differential equation, we're able to you know, be able to answer these interesting questions. Now, I will say on the right-hand side, I can almost hear the right-hand side of this differential equation talking to me. Not quite, but, you know, could we rewrite the right-hand side of the differential equation? Nathan, what do you think?
I was going to ask a question separately.
Yeah, what could we do to the right-hand side? to make it a little more, maybe a
Factor.
little more easy. Factor. Good. Jacob, did you say that?
No, that was Maria.
Oh, Maria. Oh, Maria. Okay. You're right, Maria. And Jacob has the right idea too. All right, we're going to factor. Good, good. Okay, so let's go to the solution and let's see what happens here. Okay, very good, very good. Okay, a little analytical thinking here. So indeed, what I do is I factor out the common factor of 1.2p. Okay, I factor that out. And so dp dt will equal 1.2p times 1 minus p over 4,200. Now population, we're assuming population is positive, because if population were equal to 0, well, that would mean you have extinction, right? You don't have a population. So just for, I mean, sometimes though, we have to consider, hey, the population could be 0 because there are extinct populations. But if we look at these factors, the 1.2p, okay, the 1.2p generally is always what? That factor is always
Positive.
that's right. Good, Nathan. Always positive. However, the 1 minus p over 4,200, that factor could be, well, it can be positive or it could be negative. Or, or it could be even 0, right? So what I mean is that factor could be positive. Well, let me be more clear. The first factor is going to either be positive or 0. The second factor, let me write it again here. Hold on. Let me just write it again. So the first factor, 1.2 times p, okay, and actually we don't even need to do 1.2. We know 1.2 is there. We could just focus on p. P can be positive or it could be 0, but you're not going to have a negative population, okay? The second factor, 1 minus p over 4,200, that could be positive, that could be negative, or that could be 0. Okay, so let's now, given that, let's see what happens. So, okay, dp dt will be greater than 0 when p is between 0 and 4,200, based on the second factor. Okay, so of course, the first factor, the p, would be positive if p is between 0 and 4,200. But if you think about the second factor, okay, when is 1 minus p over 4,200? When is it greater than 0? That's greater than 0 when 1 is greater than p over 4,200. And that would be true when 4,200 is greater than p. If we can multiply both sides of this by 4,200, right? And it's positive, so it doesn't change the inequality. So that means p is less than 4,200, and so that shows why this is true. The derivative will be, rate of growth will be positive. The growth rate is positive when p is between 0 and 4,200. Are there any questions on that? Okay, well, let's continue on then. Now, the growth rate is negative. The growth rate is negative when p is greater than 4,200. again, what you can do is you can say, well, all right, so when is 1 minus p over 4,200, when is that factor less than 0? Because that would make the derivative negative, right? Well, that means 1 is less than p over 4,200. And so if you multiply by 4,200 here, trying to just squeeze it in, you know. This isn't raised to a power, this is multiply. 4,200. You'll get 4,200. 4,200 is less than p. And so there is, or p is greater than 4,200. Are there any questions on A or B? Okay. Then finally, the derivative will equal 0 if p is equal to 0 or p is equal to 4,200. So 4,200 is what's called a carrying capacity for the population. Okay, that's what a carrying capacity is. If the population reaches 4,200, then the growth rate of the population is equal to 0, and that means the population stays constant with time t, right? So as time goes on, the population doesn't grow or decrease; it stays constant. We know that when the derivative of a variable, when we know when the derivative of a function is equal to 0, that function has to be a constant function, right? Now I want to be a little careful on that, but that's fine. That's fine. So how many have noticed that, like, populations? I mean, why would a population have a limitation? Why would it have, why would it have a carrying capacity? Why don't populations just grow and grow? That's right, Nathan. There's a limitation on resources. You might be able to model a population, for instance, exponentially for a period of time, but after enough time passes, the population will grow. But the population, because of limited resources, after enough time, the population won't be growing exponentially anymore. So let's look at a chart here. Let's look at a graph of possible solutions here. Well, first, are there any questions on what I did here? Are we okay with this? Okay, Nathan's good. Jacob's good. Okay, well, then we'll go to the next page here. So this here is a graph of what possible solutions look like to the differential equation. So I've not taught you how to solve a differential equation yet, right? I've not taught you how to solve a differential equation. But, for instance, if you had an initial population, so you see the x-axis here, well, it's a t-axis. T goes from 0 onward, okay? And p is your y-axis, that's your population. So if, for instance, you were to start out at a population of 6,000, let's say this is like a population of deer, for instance, okay? Population of deer. How many have seen some deer running around from time to time? Okay, all right, many of you have, and you notice they're not all over the place, right? Because there are limited resources. But let's just say that we have 6,000 deer. Well, and I'll come back here. We know that if our population is greater than 4,200, then the growth rate is negative for the population, and that means the population has to decrease with time t. It has to decrease with time t. So when we have 6,200, if we have 6,200 deer, for instance, well, and let's say that the deer population followed this, we could model the deer population with this differential equation. The deer population is going to decrease until it reaches what? The deer population decreases, okay, until it reaches the 4,200, because 4,200, that's right, Jacob, 4,200 is the what? It is the equilibrium, that's right. So that's right. So this is what a typical solution to the differential equation would look like if we had an initial population of 6,000. It's what's called an initial value problem. Are there any questions on that? Okay, well, let's suppose the deer population were 1,000. Okay, maybe, for instance, you know, winter took its toll on the deer population, and here in the spring we have 1,000 deer. Well, okay, what happens when population is 1,000? Let me go back to the thing here, back to the first page. We know that if initial population of deer is anywhere between 0 and 4,200, the growth rate, the rate of growth is positive. Okay, and that means that population increases with time. So the population will increase with time. Now, what it'll look like here, okay, what it'll look like if we start out with 1,000 deer, initially the population will increase exponentially, okay, because there's a lot of resources available. But what's going to happen is eventually with time, the population is going to level off and reach the equilibrium or the carrying capacity. And it will stay there unless, you know, I mean, with this simple model, it'll just stay at 4,200. Now, what happens in 282 differential equations is you look at models like these, and then you have other factors like harvesting and things like that. Hunting, you know, if you hunt the deer, what will it do, you know, to the population and things like that. But this just gives you an example of if we know a differential equation, we can actually see what typical solutions look like to the differential equation, given different initial values. We can see what typical solutions look like without actually solving the differential equation, and that's called qualitative analysis. Now, what we'll learn on Thursday's class is we'll learn more about differential equations. We'll be continuing our discussion. But are there any questions on this before I know we're, you know, at our time here. Are there any questions? Okay, let me stop the recording.